want to say two more things about Kirchhoff Laplacians on quivers. So quivers are graphs where also multiple connections and self-loops are allowed. And this allows us also to model magnetic Schroedinger operators where we have functions additionally given on vertices and on edges. The edge part is the magnetic part and the vertex part is just the usual potential part. But first of all, about the theorem. So here I already wrote that down last time and we looked at the proof. The proof cannot be simpler. It's essentially just the Gauchi Interlace Theorem, which allows you to use induction. So the eigenvalues, the case eigenvalues of a Kirchhoff Laplacian of a quiver can be estimated by the vertex degrees. So the vertex degrees are counted by looking at loops, first of all, and also connections. So in this case, the vertex degree is 1, 2, 3, 4. Also here I've written down another quiver and I wrote you down the gradient. So we have a calculus on it, we have gradients, we have divergence, of the gradients, which is the Laplacian, and then we have a relation between the eigenvalues and the diagonal entries of this Kirchhoff Laplacian. There is also a lower bound which I did not mention last time much, and it's essentially there's a stronger estimate by Brouwer and Haemers, which I cannot reach yet for quivers, which is just adding 1 here. But this is sharp for example, for complete graphs. For complete graphs, every decay is n-1, so the eigenvalue is 0, so that's sharp. And Brouwer and Haemers really point out this is essentially the only exception. So that, of course, when you have exceptions, it makes it harder to get started. And so I have here a little bit of weaker bound, but it's universal. It's for every quiver. We have this bound here. And as I mentioned, it's a simple proof by induction. So you assume you have proven it for n quivers with n vertices, and then you prove it for quivers with n+1 vertices. So what happens is one of the estimates is immediate for every n except the lambda n+1, which is the highest eigenvalue, which is the spectral radius, which we have to estimate separately. And the lemma here, and essentially Anderson-Morley powerful idea that this supersymmetry, that the divergence of the gradient, this Laplacian is essentially isospectral up to 0 eigenvalues to ft, which is the one-form Laplacian. So one-form Laplacian are functions on edges, and this is kind of a magnetic potential. It's a one-form, and when you have a magnetic potential, you can take the derivative, exterior derivative, which is a function on triangles, and that's the electromagnetic field which you have on an arbitrary graph or quiver. So this is pretty cool. You have that framework in the discrete also, and it's not as awkward as in the continuum where you have to deal with sheaf theoretical constructs, which is here. It's just nice matrices here in the finite case, especially these are finite matrices. So I myself was very interested when I was younger in Jacobi operators, and especially in the Jacobi operators, which have also a side diagonal, non-trivial side diagonal entry, and it's would be very good to have eigenvalue estimates there. These would allow you to compute or estimate the determinant, and then you could estimate the determinants of arbitrary Jacobi matrices. You could solve an important problem in ergodic theory, which I worked on for 15 years. Could not do it. It's the entropy problem of the standard map. And it's essentially a problem about determinants, because the Lyapunov exponent is the logarithm of a determinant, and by Pesin theory, the Lyapunov exponents are related to the entropy, to the metric entropy. So it's a linear algebra problem essentially. You can use this also to estimate eigenvalues of matrices which have real values, and that's one of the points I wanted to make. So there are 2 points I wanted to make today. First of all, say something a little bit more about the lower bound, which is actually also by induction, you have only to verify for the lowest eigenvalue. So the ground state, that's what you have to do. You have to estimate, if you have that, then also by Gauchi's interlace theorem, this holds for all lambda, you can use the induction. Here, essentially what happens if you go with n to n plus 1, and then if you remove the lowest d1, then the k becomes the k plus 1. So that stays the same, and this kind of goes to k plus 1, the lambda goes to lambda plus 1. You can use still the induction. So it's a very nice proof, so that you have essentially the same argument for the upper bound and the lower bound. But this one, I have to explain this a little bit. So in general, because of the FFT or FTF, this has non-negative eigenvalues. So the only case which you really have to verify is if the D1 is bigger than n minus 1, bigger than n minus 1. Otherwise, it's clear. So if D1 is bigger than n minus 1, but then every dk is bigger than n minus 1, but you can only have n minus 1 vertex connections, you can have only n minus 1 connections maximally, and by the way, if you have multiple connections, if you add another edge, so if you take the Kirchhoff Laplacians of this and you add another edge, kind of you double up, then by the Hadamard variation formula, you immediately see the eigenvalues can only go up. You can explicitly tell from the lowest eigenvector, you can tell how much it is going up. The derivative is always positive, and you just add to make a change here. If you slowly add here more and more value, right, from 0 to 1. So this goes on here. This is pretty, actually all eigenvalues that can only go up. And also if you add a self loop, this is only the eigenvalues can only go up. But so that's essential. But once we have kind of this, that there are loops at attached at every, if there's, for example, 2 loops attached at every vertex, you can just take 2 times the identity matrix away. So this removes the lowers the eigenvalue by 2 and also lowers the dk by 2. So you can then make induction for proving that. You can use induction with respect to the number of loops which you have also. The second thing I wanted to point out is the relation between quivers, or Kirchhoff Laplacians of quivers, and these magnetic operators. So classically, if you have a magnetic operator, that's kind of what you are dealing with. You have a magnetic vector potential which produces then a magnetic field, and you look at the eigenvalues of these operators, and so that's the discrete version. Is just you attach also integer value or kind of arbitrary values at the edges or at the vertices. Now, in order to have a quiver, so these values have to be positive here, so that the side diagonal, kind of in the side diagonal, if you look at the side diagonal, these are negative values. So you can add as much more as you have. Of course, this also affects the diagonal elements, but and you can take care of the diagonal elements with loops. So this assumption that they are actually kind of integer valued is not really relevant. Also that they are positive. Actually, that this is positive doesn't really matter much, because you can just take the coordinate system of the energy. You can move around, so that this becomes this becomes positive. And what I wanted to say, first of all, I mean, these are integer values, right? We have integer values here on the edges and integer values on the vertices. But once you have such an operator with integer values, like here, this would be such a quiver. This actually produces a periodic Jacobi matrix, right? So 2, 3, 4, 5 times 5 matrix with a side diagonal, so periodic Jacobi matrix here. And so with that, with the number of loops, you can control the diagonal elements, and with this you can control the side diagonal elements. For example, you can approximate with rational ones, and then for rational ones you can deal with integer valued matrices, and this estimate doesn't really change. If you scale things, for example, you divide the matrix by 3, then this changes the eigenvalue by 3, and it also changes the diagonal elements by 3. So it's kind of an almost obvious observation. But what I really like is that you have a geometric object only. So the geometric object actually incorporates also a magnetic field and a scalar field. So it's kind of nice to have this this framework here of quivers, and it's for me especially kind of attractive because we have this lemma here which tells that if you take a Kirchhoff matrix of a quiver and we delete the case row, case column, what happens is we have again a Kirchhoff matrix of a quiver. We just take away the vertex which we have, and we add additional to everything which we connected, we add additional loops. So that's how we deal with principal submatrices, and because we are closed, we have a system which is closed on these principal submatrices, we can take directly, we can apply the induction directly in that framework, and we have not to artificially introduce, close the set of matrices like I did in the original paper. And so the proof here becomes much more relevant. I think it's this actually kind of another remark is that this shows that it's actually also interesting for other reasons. If you're interested in Schroedinger operators, this can be useful. For example, with this, I can estimate you the entropy from above of, say, the standard map. Of course, you can estimate it also differently, but of course, we would like to estimate it from below. So I expect here to have something much better also, which is which still holds for all quivers. But so this is done for graphs by Brouwer and Haemers. That's what I wanted to say today.